So, welcome back. In the last video, we have seen the weighted resistor type of digital to analog converter. And in this one, we will discuss about the R to R ladder type of digital to analog converter. We have seen that the previous one had two disadvantages. The first one was it required too many number of resistors of different values. The second thing is getting so accurate values of resistors was a tough task. So it was not suitable for any digital ladder which has high number of bits. And this particular R to R ladder type of DAC, this overcomes the disadvantage of these two. As the name itself suggests, it has an R to R type of ladder type of structure where it employs only two different types of resistors. One is R, the other one is a multiple of that R, double the value of that initial value of R. So it develops an analog output which is equivalent to the binary digital input using this R to R ladder type of structure in the inverting adding circuit. So first of all, let me show you the figure. This is the figure of a 3-bit R to R ladder type of DAC. If you carefully see, this is just like, so this is an op-amp which we have seen, which has a virtual ground. Since it is grounded, so this one will be also at ground with no current flowing into the terminals. And see, the inverting terminal is connected to the reference voltage using an R to R type of ladder type of structure. See here, R to R, yeah, see this is initial to R will be there. This is R to R, R to R, and to R, and this is your R structure. Okay, so it is just like having a ladder type of structure. And coming to the operation, see the digital switches, they will be connected to the ground if your corresponding input bit is 0. As we know that either it can be 0 or 1. If it is 0, it will be connected to the ground, and if it is 1, it will be connected to your reference voltage or reference current. Okay, it is very difficult to get the generalized output voltage equation of this R to R ladder type of DAC. But we can find the analog output voltage values for individual binary input combinations easily. So let's try for one particular thing. We'll try for, let us suppose, if it is just like 100. Okay, if it is 100, what will happen? See, which means that B2 is 1, which means that it is connected to directly here, and here it is connected to ground, and here also it is connected to your ground. Okay, so this is so which means that I will redraw the circuit here for, this is 2R, again 2R, it is grounded. So this corresponds to B0, okay, and this is R, and again 2R, which corresponds to B1. Since it is B1 is also 0, I am connecting it to the ground. R, and again this is B2. B2 is 1, so I am connecting it to minus VR. This is 2R, and this is R, which is connected to your inverting terminal of op-amp. The non-inverting terminal is grounded, and here you are having a V0. This is my 2R circuit. Okay, so now this is my circuit. Let us try to determine the equivalent analog value. Now, as you know that this is a virtual ground type of connection, so automatically here also you will be having a 0 voltage. So if I write KCL at this particular point of A, so before that, see here, 2R and 2R, they are in parallel, right? So this is a combination, parallel combination. I'll get an equivalent of R. R again in series with R, I'll get 2R. 2R again, it is in parallel, again I'll get R. R again R. So this is also grounded, right? 2R. So here, up to here, what I am getting, it is up to here 2R. And again here I am having 2R, but this one is connected to my minus VR, and this is my R, and this is my virtual ground, so I will ignore this one. I'll take it as 0 here. Okay, and here again I do have 2R, and this is my output, and this is my A point which I'm considering. So I'll consider this another point as B here for our convenience. So at B, what is my KCL if I do apply? This is 0 minus 0, right? Sorry, VB minus 0 by 2R plus VB minus of minus VR, I'll get plus VR by 2R plus VB minus VA by R is equal to 0 at this particular one. At this particular node, see, it is VA minus VB, VA minus VB by R plus VA minus 0 by, there is nothing, right? So no current will go into this one. Okay, plus here it is VA minus V0 by 2R is equal to 0. So from these things, if you know the value of R, you can determine what is VA and also what is VB, and you can obtain what is the value of V0 also. Okay, so you can eliminate VA and VB, and you can get your values of V0 in terms of VR in this particular equation. Okay, so this is a simplified mechanism of how to determine V0 in terms of VR. Okay. So one more thing is this is a 4-bit type of structure. If you carefully see, this is another typical structure of R2R ladder DAC. Okay, and next is see the advantages. As already said, it contains only 2 values of resistors, R and 2R. So it is easy to select and design more accurate resistors. And if a greater number of bits are present in the digital input, then we have to include required number of R to R combinations additionally. Okay, so the circuit may look a little bit tricky, but we can try to solve the problem easily. So when compared to the conclusion is that when compared to the previous type of DAC, an R2R ladder structure gives us more advantages as it includes only 2 different types of resistors. Okay, so I hope that now you are able to compare the operation of weighted resistor and also R2R ladder type of DACs, and I hope that you will be able to determine the analog output voltage corresponding to the given digital inputs. Okay, and these are the practice problems. We solve them at home, and we will discuss more things in the class. Thank you.